Lesson 4: Turbines, Exhaust, and Engine Architectures. After combustion, hot gases must be converted into mechanical energy. Just before reaching the first stage turbine rotor, the gases pass through nozzle guide vanes. These convergent passages accelerate the flow and turn it to the optimum entry angle. Under high power, the flow at the vane throat reaches local sonic velocity, known as choked flow. The hot gas then impacts the turbine blades. To survive the extreme environment, these blades utilize convection, impingement, and film cooling using compressor bleed air. They are often attached to the rotor disc using fir-tree root fixings, which feature multiple interlocking serrations to distribute high centrifugal loads and accommodate differential thermal expansion. Without these protections, blades suffer thermal creep, a permanent plastic elongation caused by high temperatures and centrifugal stress. In a dual-spool engine, the high-pressure turbine extracts energy specifically to drive the high-pressure compressor and the accessory gearbox. The remaining energy dictates the engine type. In a commercial high-bypass turbofan, the low-pressure turbine drives a large fan. This design accelerates a larger mass of air to a lower velocity, giving higher propulsive efficiency and lower specific fuel consumption at subsonic speeds than a pure turbojet. In a free turbine turboprop, the power turbine driving the propeller gearbox is mechanically independent of the gas generator and driven purely by expanding exhaust gases. Finally, any remaining gas exits the aircraft through a propelling nozzle. In subsonic aircraft, this nozzle is convergent, accelerating gas velocity up to a maximum of Mach 1 at the exit to provide final thrust.